conference. And it is a pleasure to introduce our next speaker, Professor Peter Littelmann from University of Cologne. And he will tell us about Seshadri stratifications. Please, you may share your presentation.
All right.
Okay, we see your screen.
Yeah. Sorry. Okay. So now everything was okay? Okay.
Yes.
Okay, first of all, I would like to thank the organizers for the invitation to give a talk at this very special conference. I would also like to mention that this is a report on joint work with Rocco Kiribi and Xin Fang, Rocco from Lecce and Xin Fang from Aachen. I will assume throughout, that was too fast. I will assume throughout the talk that K is an algebraically closed field and X is an embedded projective variety, and variety means for me always irreducible. And I will assume that it is always smooth in codimension 1, which means that the singular set has codimension at least 2. So before I go into the details, let me give you a rough idea of what a Seshadri stratification is. Okay, first of all, it's a collection of subvarieties and a collection of homogeneous functions. And they will have to satisfy certain compatibility conditions, which I will explain next. And the indexing set of these varieties and homogeneous functions, it's the same indexing set. I will always assume that it is a finite set. And the functions which we have chosen, they would play a special role in this construction. So we will always call them extremal functions of the stratification. So what is a Seshadri stratification good for, or why should I care about it at all? So a rough idea is that the Seshadri stratification gives a tool to attach combinatorial objects to my projective embedded variety, and the hope is that it is useful to study the geometry of X. So for example, if my variety admits such a stratification, then one can always construct a flat degeneration of the variety into a reduced union of projective toric varieties. Okay, here, please note that toric variety means, of course, it's an irreducible variety, but toric does for me not imply that the variety is normal. Actually, in general, the degenerate variety will not be normal. In nice cases, well, can even do more. For example, one can construct a standard monomial theory for the homogeneous coordinate ring of the embedded variety. Okay, after this quick survey, let us now be a bit more precise. So recall, the Seshadri stratification on my variety X, this was a collection of subvarieties, and let's now have a closer look at these subvarieties. First of all, note that my indexing set becomes automatically a partially ordered set by just saying that P is smaller or equal to Q if the subvariety in my collection XP is contained in the subvariety XQ. So the condition S1 on these subvarieties is, like X itself, I will always assume that these subvarieties are smooth in codimension 1. I always want that X itself is an element in this collection, or another way to say it is that A has a unique maximal element, and the subvariety which is attached to it, this is my variety X itself. I want that the subvarieties corresponding to minimal elements in this partially ordered set, that they are points. And then I have something like a flag condition. I mean, whenever I have XP is XQ is contained in XP, and this is not of codimension 1, then I want that in my collection of subvarieties I can find other ones which I can squeeze in between so that I get a flag of varieties contained in each other, always by codimension 1. Okay, so let's look at an example. So let's start with something simple. I take P2 and the corresponding hyperplanes. Or in other words, I take X as my P2, I fix the standard basis of K3. My indexing set here is the set of all subsets of 1, 2, and 3, which is not empty. And to such a subset, I associate the coordinate plane or just the line, which is generated by all basis vectors such that the index is an element in P. And as subvariety, I take the corresponding projective space over this. So I have, when I draw the Hasse diagram, I have here my variety X, which is just the P2. It's the subspace spanned by 1, 2, and 3, E1, 2, E2, E3. So this is my full P2, or I take a subset 1 and 2. Then I take the corresponding basis vectors, E1 and E2. I take the span of this, and then I take the projective space over this. And we see in this collection of, we have the big variety, we have the coordinate hyperplanes, and we have their intersections. We see that all these subvarieties are smooth. I have a unique maximal one, which is the variety itself. The minimal varieties, they are just points. And from the Hasse diagram, we also see that immediately that the flag condition is satisfied. So here another example, we take the Grassmann variety of D-dimensional subspaces of Kn. I take it, embed it via the Blicker embedding, in the projective space over which D of Kn. So in this case, we have always this famous indexing set of strictly increasing sequences of length D between 1 and n. The subset, for example, indexes the canonical basis of which dkn, but it also indexes the Schubert varieties, which I can find in the Grassmann variety. And I take, in this case, as collection of subvarieties for my X, namely the Grassmann variety, I take just the collection of all Schubert varieties. It is well known that the Schubert varieties are all smooth in codimension 1. I have a unique maximal Schubert variety, which is the Grassmann variety itself. And I have as minimal element just 1 point. There's only one Schubert variety of dimension 0. And it's also well known that the flag condition is also satisfied in this case. Okay, here for lovers of Schubert varieties, for simplicity, let's assume my characteristic K is 0, so I don't have to worry about problems in representation theory. So let G be a simple algebraic group. I fix a Borel subgroup and a regular dominant weight, and I take an embedding of G mod B into the projective space over the irreducible representation of highest weight lambda. So then I have an embedding of G mod B in there, just as the highest weight vector. Then I fix a Weil group element. And then I take as my X this Schubert variety itself, which is contained in the projective space over a de Mauzière module, which is a submodule of my representation. So as my indexing set, I take A, the set of all elements in the Weil group, which are smaller or equal to W. And as my collection of subvarieties, I take all Schubert varieties which are contained in my fixed X of W. And again, it is well known that Schubert varieties are smooth in codimension 1. I have a unique maximal variety because X of W is itself in this collection. Again, there is only one minimal Schubert variety, which is a point. And we have also the flag condition is satisfied. So these are all examples where all the conditions are satisfied. And next, let's look at another example, which we call the generic hyperplane stratification, which is the following. We take the projective variety embedded in a projective space of dimension R, which is smooth in codimension 1. And by Bertini, we know that there exist generic hyperplanes, so that when we cut down our variety now with these hyperplanes step by step. Then we get here a sequence of subvarieties which are all contained in each other. And by Bertini, we know that they are all reduced. They are irreducible, and well, if I choose them generic enough, these varieties, they are also all smooth in codimension 1. So in particular, in the last step, we have a smooth curve, and one knows that when I intersect this with with the last hyperplane, which I haven't used yet, then I get a finite union of points, exactly S points, where S is the degree of the embedded variety. So I take as my collection of varieties all these guys which I get by this intersection, and at the end, I just add all these points which I get in the last intersection. And if we look then at the Hasse diagram, then it looks a bit like a broom, because I have here also the other x02 and so on. And we see that by construction, all subvarieties which I've chosen here in this collection, they are smooth in codimension 1. I have X itself is an element in this collection. The minimal varieties, they are all just points. And also you see from the Hasse diagram that the flag condition is also satisfied in this case. Okay, so as one was a condition on the subvarieties, next comes conditions on the extremal functions. And these conditions, they concern their vanishing behavior. So let's first look at the case where I have two elements in my indexing set A. So let's say we have P and Q, and they are different. So if they are different, then I want that Fp is not smaller or equal to Q, then Fp vanishes identically on my XQ. And the other condition concerns the case when P is equal to Q. So we have here our Fp and we have here our Xp. I have here the zero set of my Fp, of my function, and I want to look at the intersection. And we see in this intersection, I want that this is a union of divisors. And these are exactly the divisors are given by those elements in my collection, which are of codimension 1 in XP. Okay, so what does it tell us? First of all, it's a union of divisors, so it means that the Fp does not vanish identically on XP. Secondly, by the second condition, since XQ is of codimension X1P, we know that these Fp's vanishes anyway on these guys. And the condition is that this is, at least set theoretically, exactly the vanishing set of my Fp once restricted to XP. And now we see the Seshadri stratification on X as a collection of subvarieties, where A is a finite indexing set and you have a collection of homogeneous functions, and they should satisfy these three conditions S1, S2, and S3. Okay, to digest all these definitions, let's look again at examples. So the first example we have had already, this is we take our P2 and the coordinate hyperplanes. So you see here I have chosen some functions. And the rule is the indexing set tells me that I take as function the product of the corresponding variables. So what is the vanishing set of F1, 2, 3? In this case, well, we know either X1 vanishes, then my point must be a linear combination of E2 and E3. So we get this guy. Or X2 vanishes, then my point must be a linear combination of E1 and E3. So I get this guy. Or I take a linear, or I take my X3, and then it vanishes if and only if my point is a linear combination only of E1 and E2. So I get this guy. So we see exactly that in this case, the vanishing set is exactly the union of the three divisors which are in my collection of subvarieties. And if we look here at this guy, F1, 2, then the function is X1, X2. And then we see again, the zero set of this is either X2 is 0, then we get this guy, or x1 is 0, then we get this guy. So again, we have here that the vanishing set is exactly the union of these two devices, but we also have this compatibility condition with elements which are not compatible. So we have 1, 2. This is not compatible with this guy, with 1, 3. But x1, x2, well, x2 vanishes. So my function vanishes exactly on this guy. And x1 vanishes exactly on this one. So we see that also the condition S2 is satisfied in this case. So next, another example. Let's go back to the Grassmann variety. We have taken as collection of subvarieties the Schubert varieties. And as I said, that's indexing set of strictly increasing sequences between 1 and n of length d. There's also an indexing set for the canonical basis of wedge dkn, and hence also of its dual basis, which are the Plücker coordinates. So I take as collection of extremal functions just the Plücker coordinates, and then it is well known that these two conditions S2 and S3, they are satisfied. Now, this does not only hold in the case of Schubert varieties and Grassmann varieties, so it's actually general. So let's go back to the other example we had, where we have a Schubert variety embedded in the de Maussure module of an irreducible representation. So I have now to explain to you what is the replacement for the Plücker coordinates. Okay, what do? I take a highest weight vector. Then I go to the dual space and take f lambda, the dual vector to v lambda. And then for any Weil group element, I just take the Weil group conjugate of this function. And this I take then as a collection of extremal functions. I take these so-called extremal weight vectors, which are associated to elements in the Weil group, which are also elements in A. And also here, it is known that these extremal weight vectors, they satisfy these conditions S2 and S3. Okay, and now let's go to the embedded projective variety of dimension R. So the case which we call generic hyperplane stratification. So we had these generic hyperplanes. We had then our collection of subvarieties. These are the varieties we get by intersecting my given variety successively with all these hyperplanes. So we have here the irreducible part we get, and at the end we take just the union of these points. Now these hyperplanes, they are defined by linear functions. So as my extremal function for this collection, I just take the defining equations for these generic hyperplanes. So what is left is to find functions which correspond to these points. And I leave it as an exercise for you to find these functions. Note that in this case, it's not so complicated because, well, we just have a point. So these conditions S2 and S3, which look rather involved, become very simple. They just mean I have to find a function. Let's look at this example, F01, which does not vanish in the point x01, which vanishes in all other points. So I have to do the same for x02. I have to find a function which does not vanish there, but vanishes in all other functions. And this gives me then a Seshadri stratification. So in particular, we see that every embedded projective variety, as long as it is smooth in codimension 1, it admits a Seshadri stratification. Of course, this Seshadri stratification is far from being unique, and it really depends on the construction. Okay, so what is this data good for? So what we want to do is we want to define a filtration on my homogeneous coordinate ring of my embedded varieties. And so there are two steps in the construction. The first step is I want to use valuations to define filtrations. So for every maximal chain in my partially ordered set, I want to define a valuation on my homogeneous coordinate ring. Okay, so let's start and fix a maximal chain of elements in A. So then I get a flag of subvarieties. So just to simplify the notation, let's forget about the P's and just take the indices. And while we also have a collection of extremal functions. And now I define evaluation as follows. So let's go to the affine picture and replace my embedded variety by its affine cone. So here a very rough idea how this works. I start with a regular function on my x. Then I have in my chain, I have the next smaller variety, which is the divisor. And then I remember what is the vanishing multiplicity at this divisor. Okay, now I have left my collection, also my external functions. I know that my external function fr vanishes on this divisor. So let's assume we can find an appropriate power so that h divided by this power of my extremal function has vanishing multiplicity 0. So I can restrict it to this divisor and it becomes a rational function there. So then I proceed with this, namely, I know in my maximal chain, I have here another variety, which is a divisor in this one. Now I remember of my new function, the vanishing multiplicity, which might be negative, it might have a pole in there. And then I do the same thing. I take now this function and construct a new function which lives then on the next smaller divisor, namely I divide it again by an appropriate property, by an appropriate power of an extremal function, and then I proceed. Of course, there is a lot of cheating here in this case, because first of all, it's not at all clear that such a power here exists, but one can adapt the construction. So this is the idea how one should do it. It doesn't work always, but there is a way to get around it. Another reason why I'm cheating is that actually the valuation which I want to have is this. So I have to divide these nice integers, namely these vanishing multiplicities or pole orders, by some strange numbers. And these numbers again have to do with my extremal function, namely it's always the vanishing multiplicity of the extremal function in the same divisor. Okay, so now you can of course say, why in the hell does anybody want to replace integers by rational numbers? Sounds stupid, but what is in the background in this construction is the evaluation theorem, which is due to Ries, and which somehow connects two different valuations, or respectively quasi-valuations. So when we have a maximal chain, then let's say we end up in our XP, and then in my XP, I have all these divisors, and then I have to choose one. Okay, so in every divisor, when I choose it, it gives me a valuation, namely by saying when I start with a regular function on XP, I remember the vanishing multiplicity along the chosen divisor. So this always gives me integers. Now there is another option, which are called the so-called Ries valuations, which are defined in the following way. So instead of looking at the divisors, I take the principal ideal, which is generated by my extremal function inside this coordinate ring of the affine cone over my XP. Then I define quasi-valuations in the following way. Here, starting with a regular function, I look for the maximal power m so that h lives in I square, I cube, and so on up to im. And this number I remember. Okay, one can show that this is a so-called quasi-valuation. So quasi-valuation means always, instead of having the valuation of the product of two functions at the sum, by quasi-valuations, I want to get an inequality. Okay, but this quasi-evaluation was not good enough. So people considered kind of limits. So you not only look at the quasi-evaluation for h, but also for its power. But then you divide by the corresponding power and take the limits for k going to infinity. So I can show that this exists, and it's actually a rational number. And the evaluation theorem by Ries connects these two. It says I can either calculate this guy here by using this limit procedure, or I look at what I first was looking at. I was looking at these vanishing multiplicities and all these divisors. But this is not enough. I have to divide these values exactly by these vanishing multiplicities. And this is the way these two things are connected. So here again, just as a reminder, the difference between quasi-evaluation means here only I have an inequality. Okay, the second step is, well, I have a partially ordered set. So in general, I have a lot of maximal chains. And there is no reason why one maximal chain should be better than any other one. So I want to look at all of them at once. Okay, so how to do this? So I take my partially ordered set A, I fix a total order on it, which respects the partial order. I take a big vector space QA, and I do it with the Lex order as a total order. So I have a totally ordered vector space. And so far, my valuations, they always were valuations with values in such a subspace. And I now, from now on, I consider these always as the subspace of my QA. They are spanned by those basis vectors whose index is an element in the maximal chain. And here now we have a definition and proposition. So to have, so to say, all valuations of the same value, or no, how to say, the same, they should be all equal in some sense, equally worth to be considered. I look at them all at once. So I start with my H, I attach to this collection of elements in this big vector space, which is totally ordered, so it makes completely sense then to look at the minimum. And well, it's well known that when I have a family of valuations and I take and then I apply the minimum operator to this, then what I get is not anymore in general a valuation, but anyway, it's a quasi-valuation. So that's the definition. So the proposition is this tiny little index here, which tells me that the value which I get is always non-negative. So all entries of this result will be non-negative. And this is quite an important point and very helpful later. And actually, this is a direct consequence of the Ries valuation theorem when you look at the proof. Now, when you consider the construction, you may say it looks quite a bit like Newton-Kunkov theory. Actually, it is up to some certain point. Only with the difference that at the we end up only with a quasi-valuation. But also here is another point. When you look at Newton-Kunkov theory, you usually have one flag, and then you always add as an extra point the degree of the homogeneous function. So you never consider just the valuation of your function, but you add also the degree of the function. And this is something we do not need here because somehow the degree is hidden in the result. So when I take H, a homogeneous function, and if my quasi-evaluation takes this collection of rational numbers as value, then the degree can be reconstructed by just, so to say, put a weight on these values just by multiplying with the degree of the corresponding extremal function. So in this way, we get back the degree of my homogeneous function. Okay, so what is this quasi-evaluation good form. Quasi-evaluation and induces the filtration of my homogeneous coordinate ring. Actually, in some sense, quasi-evaluations and filtrations are different words for the same thing. Now, this quasi-evaluation has some nice properties. For example, the filtration, which I get, has at most one-dimensional leaves, and they are indexed by this subset of QA. Namely, I take the evaluations of quasi-evaluation of all H and K of X, which are homogeneous. Okay, now here comes the difference. Since I only have a quasi-evaluation and evaluation, if I had a evaluation, I would know that gamma is a semigroup, or more precise, a monoid. But since I only have a quasi-evaluation, I don't know this a priori. So next, remember that by definition, every V of H, so the variation, they always contained in some of these QCs, these subspaces of QA. So when I take the intersection, then it is clear that my gamma is just the union of these QC. And of course, since I have a finite set, this is a finite union. So the point is that these gamma C's, first of all, they are semigroups, or more precisely monoids. This is what we can show. And the very important point on this is, in some sense, a consequence of the non-negativity. They are finitely generated semigroups. So if you know Newton-Kunkov theory, then you know that's always a big problem, that when you start with your evaluation, you get a semigroup, but it's hard to prove in general that this is finitely generated. So here we get this completely for free with our construction. The price we have to pay is that our gamma is just a union of semigroups. But anyway, all of them are finitely generated, so I can do geometry. That means, for example, that for each gamma C finitely generated semigroup, I have a corresponding semigroup algebra, and which means I have a toric variety. Okay, so next let's look at the corresponding K of gamma, the fan algebra, which is, well, like in the case of semigroups or monoids, we have the associated monoid or semigroup algebra. And here, when I have two elements which are not in some common gamma C, then I just say the product is equal to 0, and this is called the fan algebra. Now, I said in the first sentence, my quasi-evaluation induces a filtration, so it's natural to look at the associated graded. And here we can show that this guy is isomorphic to this fan algebra. So we have here again the nice connection. The fan algebra is more something, well, which is in some sense combinatorially defined. And we see that the filtration gives me this combinatorial object. In particular, we see that the associated graded is generated, is finitely generated. So we have a variety associated, and it's reduced algebra. And last but not least, there is also a geometric way of seeing it. Namely, we can define flat degeneration of X such that the special fiber is actually the approach of this associated graded algebra. So our X0, the special fiber, is the approach of the associated graded algebra, which is isomorphic to the approach of the fan algebra, which means it's a union of toric variety, and it's a reduced union because the algebra is reduced. And last but not least, the irreducible components of X0, they are in bijection with maximal chains in my partially ordered set. Okay, so next, well, the semigroups, we have seen I have a degree function on them, so I can associate to the semigroup again, as usual, a Newton-Kunkov body. And we can show that one can identify them with a simplex and some real spectral space. And this will be a simplex with rational vertices. So we call such a simplex with rational structure. Actually, because one can glue these semigroups together in a nice way, one can also glue these simplices together, and what one gets is a Newton-Kunkov simplicial complex with rational structure. Now, having a rational structure on each of these simplices, we can endow them with a volume, with a Euclidean volume, and we get that the degree of the embedded variety is equal to the sum of the volumes of all these simplices, and as usual multiplied with R factorial, where R is the dimension of my variety. Okay, so let me finish with some last examples, trying to convince you that one can really calculate with this. So for simplicity, again, let's assume characteristic 0, G is simple, and we have a Borel subgroup, and lambda is a dominant weight, and we have G mod be embedded in this, and the irreducible representation of highest weight lambda. So as a Seshadri stratification, we take exactly what I had mentioned before, namely the collection of Schubert varieties, and the collection of experimental functions are the extreme weight vectors. So what do these semigroups, which are the essential point of this whole construction, what do they look like? So let's fix a maximal chain, which is nothing else but fixing in my Weil group a decreasing sequence of Weil group elements. And important in the construction have also been the vanishing multiplicities of these extremal functions on the divisor. So here one has a nice formula for this, namely this is the Pierre-Chevalier formula, which gives me these numbers. I just apply my Weil group element to my highest weight lambda, then I can always find a positive root such that multiplying tau j with this gives me the corresponding element in the maximal chain, which is below it. And well, I have to evaluate on the co-root of this guy. So then the proposition tells me the following. I have here something which is actually a lattice, because I have from the Pierre-Chevalier formula these numbers, and I have these integrality conditions, namely multiplying this coefficient with BR should be an integer, here again multiplying, and so on multiplying, that should be just an integer. So this is a nice lattice, and our semigroup is just obtained by intersecting this lattice with the positive orthant. So one or the other may remember that, well, linearly ordered sequences of Weil group elements plus some rational numbers and some integrality condition. This was something which I was talking about 30 years ago when I presented the path model for representations. And in this way, we found a nice algebraic geometric interpretation of a combinatorial model for representations, namely that these indices, which I define purely combinatorial, that can be seen now this way as successive vanishing multiplicities of functions, or if you prefer, of sections. Now you may ask about what about the Newton-Kunkov simplicial complex in this case. Well, there was also Reika D, who also more or less 30 years ago, she gave a description of the path model as integral points in the simplicial complex. And the simplicial complex I defined here using our construction, what is the Seshadri stratification, is exactly the same. So we recover also here this combinatorial object. So thanks a lot for your attention. Here you find again the names of my co-authors and the paper where you can read more about the details of this construction. You can find it on the archive. Thank you very much.